So today we will be focusing on measurements, of course, of instruments. It's not going to be a lot about theory because there are already several books about theory. Some are very good also. And I wanted also to let you know that if you already downloaded the articles that are available on my website, you will see that most of the things that we will discuss today are already described in the article. So it's not going to be necessary to take notes about what you will see today. Everything is, if you are interested, on the PDF that you can download. And okay, so we go on. We have also an instrument here, so we will have also the chances to make some tests if we need it. And we proceed. We have a first part where I present the measurement system, and the second part where I will be showing you some examples of measurements that I performed on different acoustic guitars, so to have an idea also of how we can use the measurements. So I guess that we can begin. Why the measurement is the first question, of course. When I started having webinars with a guitar maker, I very quickly understood that most of guitar makers see the measurement only as a research and development tools. And for me, it's really important to specify that I guess that most of the guitar makers that are here today are satisfied, very satisfied, quite satisfied with the instruments that they make. So it's not, the measurement is not just something that we can use to improve the quality of the instrument, because maybe our instruments are already very fine, but it is something that can help us on the quality control sides. This is very important. You might have had experience of an instrument that you build and you don't understand why, but there is something strange and you cannot understand. And even if you try to understand, if you go back and read your notes, you don't understand exactly what is happening. So measurement can also be just a quality control instruments. If you don't want to change the way you build your instruments, you can begin to have measurement, to take measurements to make pictures of what you do, and to use this measurement to ensure that every instrument that is going out of the workshop is going to perform correctly. So this is very important. What kind of measurements? The most important ones, in my opinion, is the frequency response of the instruments, because it is the single measurements that give us the most important informations, and it is also quite simple to be performed. But then also the measurement of the monopole mobility of the soundboard, it's very useful, it is quite important, and it's also not very difficult to be performed. So I would say that the first two, the frequency response and the monopole mobility, are very important for each instrument that we build. The visualization of Chladni pattern might be useful, but I would say that this kind of measurement is useful mostly for R&D purposes, or to debug or troubleshoot to find some issues, for example. So these are the three main measurements that I suggest to perform, if not always, I would say very often. Then we can also use a measurement which is the bridge rotation measurement, but this type of measurement can also be included in the monopole mobility, so it's not always necessary. And wood parameters, the measurement of the wood parameters also can be interesting, very useful, but we are not going to be talking about this today, because it's a different issue. Even if very interesting, of course. But if there is the interest, of course, we can have another webinar in the future and to focus on this topic. That is, of course, yes, very interesting for all of us. So we begin with the frequency response, which, yes, most important maybe. You might have experience with this kind of graph for a loudspeaker system. Here you can see a studio monitor speaker that has a very flat frequency response. On the Y axis, you have the sound pressure. On the X, the frequency. Of course, at 50 Hertz, you have low frequencies. At 20 kilohertz, higher frequencies. In this case, The frequency response is very good because it's a very good loudspeaker, of course, and it's also quite expensive. And this measurement is taken with a signal, electrical signal at the input of the amplifier that is integrated in the loudspeaker, and the output is measured with a microphone. Of course, a flat output means that the flat signal input is reproduced without changement or distortion, if you want. And this is what we are used to see. How can we measure the frequency response of an acoustic instrument? Okay, we usually use an excitation hammer. And with this little hammer, which is a rubber, of course, we supply energy to the soundboard with a very quick and small hit. And with the software that we have installed in our computer and a microphone, we can measure via the FFT the spectrum content of that impulse. And how does it look? Here we have a typical frequency response of an acoustic guitar. This is a typical guitar, an OM guitar, Martin style, if you want. So we can have a lot of information in this graph, but we can see that it is very different from the graph that we already seen. In the first case, we have an instrument, the loudspeaker, which is designed to be faithful, to have very low distortion. In this kind, we have an instrument that is designed to produce music. And in fact, the graphic is completely different. And we have to evaluate with different keys, in fact. We can see that I also put on the graph, as you can see, 6 lines on the top. And these lines are giving us the frequency interval of the 6th string of the first fret of the 6 strings. So we can see that all the big peaks that we have in the frequency response are, in fact, within the interval that is reproduced on the fretboard. This means, of course, that it is working. It is clear. It's the acoustic guitar has been optimized during several, I would say, centuries, maybe thousands of years of development of the instrument. So yes, it is very well done. It is, the peaks are centered on the frequencies that are of most interest, but are a little bit hard to be read. So each peak is a resonance, mainly. The resonance is a quite simple phenomenon. I guess that we are all aware of this. A resonance system is a system with a spring and a mass. And the frequency, the natural frequency, the oscillating frequency of the system is directly proportional to the compliance of the spring and inversely proportional to the mass. And so the acoustic guitar, in fact, can be considered as a complex set of spring and mass systems. So in the frequency response, the first peak that we see usually is the air resonance. In this resonance system, the spring is the air within the box and the mass is the quantity of air that is inside the opening. And it is producing a resonance that is always centered around 100 Hertz, more or less. We will see later the usual frequencies. The second peak is the soundboard monopole. I can show you a quick animation. This is a finite element simulation of a soundboard of a guitar. And you can see that this is the monopole. We call like this because it's just one pole. It's like a piston moving up and down. It is maybe the most important resonance mode of a guitar. And this is usually the second peak that we can see. Then we have a third peak. We can have a third peak, which is that can be the back of the guitar. It depends on the way the instrument it is built. Some instruments are built with an active back. Some instruments are built with a back that is passive, so not active, and it's not contributing. Of course, if we want to have contribution of the back, it has to be quite light and close in frequency with the monopole, because it is excited by the resonances of the monopole. The third peak that we encounter usually is a long dipole. And this, of course, is for this type of instruments. It's an X-braced instrument, Martin type. And we can see that we have two poles. It's a dipole. And the two poles are moving in antiphase, one with each other, usually. Then we can have a cross dipole, and it's always always a dipole, but the direction is different. The cross dipole is over the 8, and the long dipole is over the length of the instruments. This is just to give you some example, because of course different instruments might have or not different type of higher order modes, resonance mode. And yes.
We have 2 questions, if you want to...
Yes, of course. What kind of USB microphone to use? Why is the frequency only max 1K? Okay, the microphone, we are going to discuss it very soon. It is on the next page. I'm going to talk about this, and I am only up to 1K because the interest that it is most important, and the most important modes that we can control in an acoustic guitars are not usually over 1 kilohertz. Of course, there is activity on the soundboard. There are modes, but usually it's not really contributing to the sound in a way that we can, I would say, evaluate or master, if you want. As you can see, at 1K, we are already 50 dB lower than the Monopole. And 50 dB means that it's very low already. I would say not really contributing a lot. Of course, there are the strings, and this is just the vibration of the soundboard. And if you want, you can measure up to 1.5 or 2 kilohertz. In these measurements, okay, we don't have standard for these measurements. And this is also one thing that we will have to discuss sooner or later. But as of today, there is no standard recognized by Association of Guitar Makers that establish the upper limit of the frequency response. So from my point of view, today, this is the best way to use the space that you have on the graph and focus on the most important modes. But of course, it can be discussed.
Giuliano,
yes.
Just a point, the video didn't work.
What video?
Yep.
I'm sorry.
We didn't see.
You didn't see the videos. Ah, no. Okay, maybe strange. Alors, just one moment. Wait.
But we guess.
So now you see the screen, right?
Yes, we see you and the chefs. Yes.
Yes. Yes.
So now you see the video. I'm sorry. So this is the Monopole, and it's the center of the soundboard, of course. This is the long dipole. And you can clearly see the 2 main modes, pole that are antiphase, and the direction, of course. And this is the cross dipole. This is the behavior of a standard Martin X-braced guitar. This is the classic behavior of this type of guitars. Of course, if you change the design of the instruments, you will change also the way the second order modes are vibrating on the soundboard. Classical guitars have different behavior, for example. But it was just to give you an example. And generally speaking, you have to keep in mind that each peak corresponds to a resonance of the instruments. And if you know the shape of the resonance, you can also focus your interest on that peak when you make the measurements. But I go on with showing you the measurement system, because we have so many things to talk about today. So the method I already said is the impact hammer method. This is a method that they use in the engineering world, of course, to make modal analysis of structures. And it is rubber. I usually use erasing rubber. And of course, the type of hammer that you will use has an impact on the bandwidth of the impulse that you supply to the soundboard. And all of these details are treated in the article published. So here we will go quickly about this because it is mainly technical, and I suggest you to download the article and to spend some time, because everything is really discussed in details in the article. The microphone is a Mini DSP microphone. Mini DSP is a company that produces hardware for the audio do-it-yourself community. And this is a microphone that is worth $100, but it's very good. It has very nice performances. It comes with a calibration file. I also double-checked the accuracy of the curve with the piston phone and the Bruin & Kier equipment that I have in my lab, in my company's lab. And it's very good. For the price, it's exceptional. Also because it's very simple. You just have the microphone and a cable that goes inside the computer. The software is Room EQ Wizard. It's a free software, very versatile, accurate, and it allows also to store the file in an articulate database. This is very important because you will be building your database during the years, and having the chance to organize correctly your files is very important for your activity. And of course, a laptop, but you know, any kind of laptop of today's can be okay. So in the picture, you see the method that we suggest. You just handle the guitar from the neck, and the microphone is 25 centimeters, so very close to the source, so to the soundboard. And the method is based on averaging. In fact, we take several measurements. It's not just one touch. We have a 32 averaging system, and this is really the focus of the system, and this is what allows to have repeatable measurements, because this is of course very important. This is made by hand, so it's not a quality control instrument. You will not get exactly fraction of dB the same result each time, but you will have dB same result each time you make a measurement. Frequency are not changing, so it's very good for this kind of application. And also the idea, compared to other systems, I am sure you have seen also very complex rig that are used mostly from luthiers that makes classical instruments, that also has makes just one touch in a point of the bridge. If you want a repeatable measurement, this is the best way, of course. But if you want to take the hand on the instrument, if you want a versatile system that allows you also to tap different parts of the soundboard, this is really a very nice system. And I have a video that I will play for you, which is the best way on Zoom. Hey, it's me. You can see the video, right?
Yeah, we will have just a question. Somebody didn't hear the distance of the microphone to the guitar.
25 centimeters.
25 centimeters.
We are in the closed field. It's important to be close, because in closed field you have a very high SPL from the source and very low reflection from the rest of the room. And so you have very good signal to noise ratio. And you have a very good frequency response. If you go farther from the instrument, you have more noise, and it's a little bit more delicate. And also, you can also go very close, and you can also go to 1 centimeter. For example, if you want to investigate a specific mode, resonance mode, you can go in different parts of the instruments. So the system automatically recognizes the microphone, because Room EQ Wizard and Mini DSP, they work together. You have a calibration file for the microphone. And so if you want to really acquire just the frequency response of the instruments, we suggest to tap the zone around the saddle. And you see the averaging, 10 averaging, 15 and 20 averaging. 25, 30. Now we are in 32, averaging. And during this time, the curve is stabilizing. And in the end, you usually have a frequency response that it is clean and accurate, in fact. And so. You see the curve stabilize as long as you advance with the measurement. And in the end, you have an instrument that it is quite repeatable. If you, of course, are interested in the actual frequency response of the instrument, so the zone of the saddle, because you can also tap around the instruments. The nice thing that I like that with this kind of system, you can also take a measurement, then you take your instruments, and I can show you. I can show you in real time because it is more simple. You still see my screen, right?
Yes.
Yes.
Okay. So now you can see this is the measurement, the window, the main window of measurement of room wizard. So I launch the measurement. So now I am in a different position than when I took the measurement before. I am on my chair and the microphone is closer to the hole here, the sound hole, and the first mode is higher in amplitude. That's because the microphone is just closer. But then I keep this measurement, and for example, I can reduce the averaging down to 4. And I can just play a note and double check how this note is positioned in compared to the resonances of the instruments. In these instruments, the first mode, the air mode, is around 105, 106. So it should be very good positioned around okay, it's around the 4th and the 5th frets. And I can see that here I am just a little bit closer to a wolf tone, just a little bit, because in fact it is in between. That's okay. And the main monopole is very good. It's exactly in between these two notes, as you can see. So it is just to show you that.
Tu as une question de Giuliano.
Yes. Okay. So I am stopping the software. We go back to the presentation. Okay. So are you dumping the string when you tap? Yes, I am with my fingers in this moment. I just kept the string with my fingers. Dump the. You can do with your finger, or if you can use little mushrooms as you prefer. Of course, it's okay to dump the string, because otherwise the string will produce harmonics in the higher frequencies. So all of the possibilities that you have with this kind of software are described in the manual. So we go on because the next topic is measurement and tuning. How can you master the frequency response, of course? Because once you have a measurement, you have to use the measurement, of course, to produce something. And for the APLG, we decided to work on the checklist, on the basic checklist. The first most important things: the frequency of the main modes, respecting the choices of the project, the distribution of the modes can produce Wolf notes, the frequency following harmonic series, and also do we have higher order modes? So we just have a look in details of these main points. Here you can see a table with what is a general distribution of the first modes, because the first 2-3 modes are the most important to define the character of an instrument. For example, is a very well-rounded instrument, the full body at low frequency, or is this a small guitar with more focus on the mid-range? Are there a lot of overtone, or the sound is more projecting? All of these things. A good part of this you can find on the distribution of the first modes. And here you can have a table where you see usually where the main modes are positioned. And of course, this is the first thing that you can see. Still, I have some example that I will show you later of several instruments that I measured and how you can relate this kind of information with the sound of the instruments when you take the instruments and you play. So this is the first thing. And the second, can we produce Wolf notes with the main modes? Because the first, but mostly the monopole, because the monopole is the mode that has usually the higher amplitude, can produce Wolf notes. The Wolf notes can be, if the guitar is very sensitive, so if the soundboard is light and very responsive, the Wolf tone can be unpleasant. When the soundboard is more massive, more heavy, it is less sensible to the production of the Wolf notes. But we hope to build a responsive guitar, and in this case we have to take care because there might be unpleasant notes on the fretboard. And so in this case, this guitar has a first mode at 106 and the monopole at 183. So this is an A string, it's open A string, as I show you. The fundamental is 110, the first harmonic is 220. So when I superpose these two, I can see that I am close to the first resonance, but with a good distance, and that also I don't have the second peak in a harmonic relation with the first. That would be here, that would mean here to have a second peak at 212 Hertz. So because at 212 Hertz, I have the second harmonic of the note, as you can see. And if I have the two main peak of the guitar with this interval, it can be overwhelming and it can be not good for the quality of the note. You have to imagine that the peak are necessary because it is what is producing most of the sound of the instruments at low frequencies, because at higher frequency there are several other phenomena, but at low frequency the first part of the bandwidth is mainly related to the resonances of the instrument. So we want to have resonances, but we have to place the resonance correctly, because the space, the most useful space to play the guitar is in between resonances. Exactly at resonance frequency, we have to be careful because this is where we can have problems. And then, of course, the last thing that is very interesting to see is the higher modes, because different type of guitar might have or not have higher order modes evident, so producing SPL, because there are always, these modes are always present. If you make a Chladni pattern, we will always find these modes because it's physical. But if the soundboard is too heavy, or if the bracing, for example, is designed to avoid higher order modes instead of producing more higher order modes, and it can be interesting, of course, it has a very, very high effect on the frequency response and on the sounds of the instruments. So this is something that we really have to take care in one way or another, of course. Always keeping in mind that in this situation, we are not talking about worse or better, because there are different kinds of instruments that make different kinds of music. So It is just about mastering and being able to understand what's happening, and if there is something wrong, to do something. And so what can we do? Oh, this is oops, there is a problem. Just one moment.
Giuliano, tu as une nouvelle question.
Does the frequency response change a lot after the guitar has been broken in? This is a very interesting question. According to my experience, no, it doesn't change a lot. And it doesn't mean that the sound of the guitar doesn't change, of course. There are a lot of things that today are still quite delicate to explain, generally speaking. And we are not trying to give an answer to every question. The starting point is that if we hear something is happening. So we try to understand, and we try to measure, we try to analyze. But if this measurement doesn't show big differences, maybe we are not measuring the right thing, the right phenomenon. So for my experience, frequency response is not changing a lot. The modes are generally speaking quite stable, even when the guitar moves, but I don't have 20 years of experience of measurement. I have 5 years of experience of measurement. This is an instrument that I built 8 years ago, and it is not moving a lot. It is moving with season, because with humidity, the changement of humidity and temperature change the shape of the soundboard, and when the soundboard is more dome, it is more rigid and it is a little bit higher. When the humidity is lower, the soundboard is more flat, and with the flatter geometry, the resonance frequency goes a little bit down. So it changes a little bit. It changes a little bit with the seasons. But I have my wife is playing a cello, and the cello of my wife is totally unstable. Each time I measure it, it behaves. It's a little bit different. But I guess that it is on the cello. You have the bridge, which is just placed. It's very high. There is l'anima inside. How do you call it? And the vibration of the cello are crazy. And so I understand that it changed, but it changes a lot. On the guitar, it's quite stable in my experience. Then the aging of the instruments, I guess it is a very interesting subject of research. So how can you shift the frequency? For the first mode, you can consider that the spring is the volume and the mass of volume of the air inside the box, and the mass is the volume of the sound hole opening. So, or you change the volume inside the box, but it is not possible when you build the guitar, or you change the volume of the sound opening, so it means the dimensions. So you can make it more deep, you can make it bigger, or you can make it smaller. In this case, for example, you see the white ring inside. Maybe you don't see, but it's I added a black and white purfling to reduce a little bit the dimension of the hole and to tune exactly the resonance frequency to 106, because 106 is rightly on the spot in between the two notes. And for the other modes, usually the springs is the dimensions of the structure, so the height of the braces or the thickness of the soundboard, and the mass, of course, is the mass of the monopole. It's not the mass of the whole soundboard; it's just the mass of the part of the soundboard which is resonating at this specific mode of resonance. So you have to modify all of this, and of course.
Question.
You should record season, temperature, and humidity while measuring and recording. Yes, of course, of course. The idea of the database. Sometimes I take out the guitar and I measure it. This is very useful to keep an instrument or several instruments as a reference. Sometimes there is something strange happening. You don't understand. Is the microphone broken? Is the connection strange? Maybe I don't have the calibration file. Something has changed. You take back your instruments. You take another measurement, and you have a reference. And also you can follow the changements during time. It's very interesting, of course. And coming back to how to shift the frequencies. reduce the thickness of the soundboard. We know this very well. Scalloping the braces on the inside. If you remove the string, you can, of course, access to the inside of the box. You can add mass on the sides. You can. The mass on this zone of the soundboard is very sensible because it's the center of the monopole. And for example, the weight differences of the pin, bone pins to plastic pins, there are almost 5 grams of difference. And it changes the resonance of the soundboard, the resonance frequency. It can be the difference to a very strong Wolf note and no Wolf note at all. So there are several possibilities, and this goes down to R&D, of course, and each guitar maker has its own formulas. But we have to always take care the fact that in fact the main modes are coupled. It means that, as you can see here, there is a mode simulator that I designed based on the Trevor Gore model of 4 degrees of freedom guitar box. And this is a little software where you can change the main parameter of the guitar, and you have uncoupled mode frequencies and resonance mode frequencies. If you change the resonance of the soundboard or the back, if there is one, you will shift also the first mode. So you have to take care because the modes are coupled. The modes are coupled between them, and it's a quite complex system. But this is, I want to say, this is something that you have to take care. But it's not even a problem. It's just this is something that you have to be aware of and experiment, of course. So now we have a Q&A because we already see a lot of things, and I am very rapid. I understand that we have still quite some things to talk about. So Q&A. Is it okay? It's Jacques Perrin. You can.
This is Adam. Can I ask a question?
Yes, of course.
So you said all these so when you remove a material on the top or in the back, does the peak go up or down?
Yes. When you remove material here.
Yes.
If you shape the brace, the peak goes down. Because the compliance also, the soundboard becomes softer and the peak goes down usually. If you increase the mass, the peak also goes down. If you decrease the mass, it's difficult to decrease the mass because usually the soundboard is already very thin, so it's not so easy to reduce the mass. But if you reduce the mass, you can go higher. Usually, it's more simple to go higher with the frequencies that go. It's more simple to go down than high because high means lighter, stiffer. So it's difficult to make it stiffer. It is difficult to make it lighter. So we should take care or not go down too much because then, if we go too much down, then going up, it's a little bit more difficult.
But I normally reduce when an instrument is finished on the sides to on the top. I remove it on the close to the sides, the material kind of with a scraper. And if I have a wolf note, I scrape until it disappears actually on the sides. And if it's a bass, I kind of do it more on the bass side, and I don't know if that's the right.
Of course, working on the side, it's important and it's useful. Because the sides are part of the system, and of course, the higher the mass on the sides, usually the lower the resonance of the top goes because it is the coupling of the soundboard, but. You have to change quite a lot the mass of the sides to have a very clear...
I remove on the top, but kind of on the connection to the sides.
Okay.
Remove.
Yes. This increase reduce the stiffness of the soundboard, of course.
Yeah. So it also moves down the peak.
Anyway, also about this on the document, there are more information about this. So I suggest to download and to have a look.
Thank you.
Other questions? We can proceed. Then we can have we will have another Q&A later. Okay. I go on. I go on. So. Okay, another measurement, soundboard mass and compliance, the monopole mobility. This is very interesting because we talk about mass and compliance, but the next step is to be able to measure this parameter. You cannot make a direct measurement of the mass of the monopole because in fact it is not the soundboard. It is just a part of the soundboard and you don't know exactly what it is. Yes, if you want, you can cut. But it's not nice and it's not neither giving you a correct result because this part, the center part of the monitor is which really contributes more to the mass. The more you goes outside, the less displacement that you have and the less contribution to the mass also you have. So the best way to measure this parameter is the measurement of the monopole mobility. You use this kind of jig, which is here. It's quite simple. It is a micrometer that is connected to this platform, so you can apply a weight on the center of the soundboard, measure the displacement, then you just plug the hole and you measure the resonance frequency. You have to plug the hole because you want the natural frequency of the soundboard, not the coupled frequency of the soundboard with the volume of the box and the resonance on the back. So you plug the sound hole, and with just very simple maths, it's here, you can have very interesting information about the weight of the equivalent mass of the soundboard, the compliance, and the monopole mobility. The monopole mobility is a parameter that gives us an indication of the facility to drive the soundboard, very simply. And how we can use this data, we will see later. The third measurement that I was talking to is the visualization of the Chladni patterns. The setup is also here quite easy. You need a sinusoidal generator that can be a smartphone app, so it's free. A small digital Bluetooth amp, it's a $30 amplifier. A small full range speaker. You need a small full range speaker because you want to be able to excite a small part of the soundboard. If you have, for example, an 8-inch speaker, you will not be able to focus on small nodes. And I show you a small video. Can you see the video?
Yes.
Of course, the Oregon is very important. Oregon or basilic, because it's the flavor. It's really.
That's funny.
No, it's very important. So as you can see, you have the frequency response in front of you. You look at the peak, and then you move around the frequencies on that peak with the speaker close to the table. And when you get close to that resonance, you can see you go a little bit high, you get a little bit down, and you can really trace very efficiently the resonance mode that it's related to that peak. And how can we use this? Of course, there are several useful applications for this type of analysis. I have an example later on. So we just proceed, and I want to show you, for example, here, if you put also a light with the LED, you can have very small lights that you can put inside the box. It's useful because you can relate, you see the shape of the Chladni patterns to the shape of the bracing inside. And this is very interesting because you will discover that you really need a very, very heavy bracing to shape the Chladni pattern differently than what the table wants to do. And usually it's the table that wins. And the second thing is that, what is the second thing? I guess that I forgot. No, it will give you a very clear idea of the part of the soundboard that is active to specific frequencies, and it can be very useful for tweaking or for modification of the frequency response of the sound of the box, of course. So I have a series of characterization of guitars that I wanted to share with you to show you with some real life example what can we see with all these type of measurements. And in this case, here we have okay, I change a little bit. So we have a very big Martin D28 and a very small Martin LX1E, the biggest and the smaller catalog guitars of the catalog of Martin catalog, and we have very interesting information. Of course, the first thing that you can see is that SPL of the D28 is much higher than the SPL of the small Martin. It produces more sound, it's clear. It has a very much lower bottom end. Of course, it's clear. The first peak is it's 106, and on the Martin is 147 hertz. It's a huge difference. And this is what we can expect, of course, from this comparison. What it is interesting also is that on the D28, we have a quite strong peak at 380 and other peak very evident at 600 and 700. This is typical of this kind of instruments. These are the two tone bars that create the asymmetry that produces this big peak and makes this kind of sound very typical. And on the Martin, on the small Martin, that has a very heavy soundboard, there are almost no signs of these resonances. As you can see, no high order modes. The acoustic sound of the small Martin is very poor. And I guess this has several reasons. The first reason is this is a travel guitar and it has to be strong. It has to be built because it is meant to be traveling with you. The second reason is that this guitar will be used very often with the preamplified output. And in this type of situation, it is better to have a heavy soundboard than a lighter soundboard because you have much lower issues of feedback. So we understand why, but it is interesting to see that with the measurement we can confirm this supposition, and we can also give numbers to this. And so we proceed. The blue curve you can recognize is the Martin the D28. In this case, the red curve seems to be quite different from the D28. It is much lower in frequencies, and we can see there are no very clear, evident higher order modes. What is this? This is a Larive D03 here, and this guitar is technically identical to the Martin. I mean, if you see these two guitars on a web shop, they will say that they have spruce top, that they have Indian rosewood side and back. The shape is exactly identical. The bridge is identical. Rosewood bridge. If you see from the outside, this is the same guitar, but in reality, the Martin T28 has 79 grams of kilo and pass, and the Larive 103. It's a big difference, and the frequency response is completely different. We are 106 and 90 hertz on the Larive, and in fact, this is due to the weight of the mass. As we say, you increase the weight, you lower the modes, the frequency of the modes. And also with such a heavy soundboard, you do not have higher order modes. And that doesn't mean that the guitar is not a good guitar, of course. My friend that is the owner of this guitar loves it. It has a very smooth sound, very smooth, because it has a very round low end, and there is no wolf tone, even if at 163 you are exactly on the high E. So it's the second E that you have on the soundboard. It's at 165. So 163, it's almost the same. It is the second fret of the first string. So it's just that you cannot define the sound of a guitar just looking at the dimensions and just specifying the wood. It is obvious for all of you, but when I see such big difference in exactly identical guitars, I am surprised. And in this case, I'm sorry, I changed the order. This is interesting also because this is the OM28, still Martin. And this, if you see, we have a very similar spectral distribution of the modes, but the Martin in green has a 6 dB lower SPL because it's very heavy. If you see, the weight of the equivalent mass of this guitar, of the soundboard, is the same as the Martin D28. It means that it is very thick, and even if this has a scalloped bracing, and so the deflection is much higher, 0.11, it means that it is less stiff than the D28. The D28 is the pre-war, it's not scalloped bracing, so it's very rigid. And the monopole mobility is similar. You will have a completely different sound because, as you can see, also there is no high order modes on the Martin OM28. So this is a guitar that is maybe good for finger picking. For strumming, why not? Because it's so heavy, so it can take some strum. It doesn't have a huge problem of wolf tone, also because 184 hertz is also much closer to close to the F at 185. It is the third fret of the first string. It's almost the same note, so it should be a very strong wolf tone, but it's heavy, so it's not really a big issue. Anyway, the guitar is not producing a lot of sound. When you compare to the D28, it's a little bit, you know, it's not so. But anyway, we look at all this measurement and we make a lot of sense about the difference that we have when we play the guitars. Here we have...
Il y a deux nouvelles questions, Juliette.
Yes. Merci, Perrine.
Deux nouvelles questions.
Stepping back to the second micrometer. I will go back later, okay? Let me finish this. So we have... this is an archtop guitar designed following Benedetto's rules, if you want. This is a very standard 16-inch archtop instruments with maple sides and back, spruce top. The thickness is around 5.5-6 millimeter on the top of the dome, back to down to 3.5 millimeters on the recurve of the guitar. And you can see that when we compare this to the Martin OM28, it makes a lot of sense also. Even if I didn't put, you know, the main resonance mode, but we can see that it is much higher on frequency, around 135 hertz at the first mode and 220 the main mode of the table. And there is a lot of sound compared to the OM28. And as the OM28, we do not have a lot of high order modes. This is typical of archtop guitar. This has an X bracing on the, under the soundboard. And so this is the typical sound of this kind of instrument. So very focused on the mid-range with less harmonics than very light flat tops. And just to finish, I have a last slide where I compare. In blue, I have this guitar, which has a very good equivalent mass. It's 68 grams for, this is an X-braced guitar. So also with, if you stay on the tradition, you can build very, very nice guitars, quite responsive also. And what is the green? It's how do you say, it's not solid body guitar, it's sorry,
semi-acoustic.
Semi-acoustic. The center of the style is ES335. The center of the guitar is solid, and we have two wings open on the instruments that produce the resonance that you can see at 400, at 600, at 1 kilohertz. There is sound produced by this guitar. even if it's an electric guitar. And the black one, can you guess? It's a Les Paul style guitar. It's very heavy. It's 4-kilogram instrument. There is absolutely no resonance over the whole bandit. The only thing is around 1.3. It's something metal. It's something related to the bridge of the instruments. And we are at 55 dB. So it's more than 50 dB lower than the sound produced by the acoustic guitar. So it's almost not producing any type of sound. So this means that this kind of analysis can be interesting also if you make different instruments than the acoustic guitars. Of course, my personal focus, it's not on electric guitar, so I didn't investigate a lot, but I guess that if you want, there is a lot of space to work also on this. If you make crossover style, different style of guitar, it might be very interesting. And about the Chladni patterns, this is an example of what you can do with. These are the last two guitars that I was building. It's nylon string guitars, almost the same. The first one is 7-string and the second one is 6-string nylon guitars. But the soundboard and the bracing type, it's very, very similar. And on the first one, I had a small issue with a string at 606 Hz. It's the high E, the 12th fret on the first string. It was resonating a lot. It was resonating maybe too much. And the sound was really penetrating. There was something strange happening. So I took the Chladni pattern and I saw that this peak is related to the tripole, to the long tripole. It's a typical resonance of the classical guitar, even if the bracing here is slightly different. And I found a solution here that was to put 5 grams of putty in this place, because this point of the soundboard is very far from the monopole. It didn't have any kind of influence on the monopole. In this case, I am recording a chord, an A chord, open, and you can see at 660 Hz, the black curve is without putty, the red curve is with the putty. And you can see that the rest of the frequency response is almost identical, and this is a very selective intervention. And this is thanks to the fact that I can see what is the resonance that is producing too much SPL, and where I can have some dedicated intervention to change, alter, or move a little bit the sound of the instruments. Okay, so we are in 1 hour of presentation, and for the moment, I would say that I am finished. Do you have questions?
If I might have a question, I put it in the chat list as well. You're talking about the equivalent mass of the Larive, for example, or the Martin. How did you calculate that? Is that with the system, with the micrometer?
It's this one. Yes, of course.
Yes, and we can do this ourselves, because I did not fully understand that system.
Yes, of course you can do. Of course.
You put a dedicated weight every time, or how does it work?
Once the instrument is finished and you have all the parts, you can do it on each step of the building, of course. The idea is that you have a resonance system, and if you want to know the parameter, so the mass and resonance frequency and the compliance, these 3 parameters are related together. So once you know the compliance is the deflection. You put 1 kilogram, you measure the deflection.
That's 1 kilogram.
Okay. 1 kilogram is the weight that I use, but around 1 kilogram is usually fine.
Okay.
You measure the deflection, which is usually in between 0.01 millimeter to 0.02 millimeters. So it's of course it's a small deflection, but this is why you need to use 1 kilogram, because if you use 200 grams, it's not enough. And once you know the compliance, you measure the resonance frequency. And there is a very simple math to calculate the equivalent mass, the mass of the resonance system. And if you need, I have this Excel file that I can share, of course, where you just insert, you know, the mass, the measured deflection, and the natural frequency, and you have the equivalent mass and the monopole mobility parameter.
Yeah. Okay. Thank you. And if you
you see the Excel?
I see you right now. I don't see the Excel.
Just one moment, because I stopped the sharing of the screen. Yeah.
Oh yeah. Wow.
So this is a simple Excel file when I put the measurement that I have, and
it just calculates the formula.
You just have to, yes, it's very simple. It's very simple.
And you showed us the Chladni and stuff, but that's all without string tension. Can you say something?
No, it's string tension is not affecting this measurement. You can do with or without.
But that's not of importance. Okay.
No, it's not really changing a lot.
Okay. Okay. Well, if you can share the Excel, it would be great. Thank you.
Of course, you can just send me an email, and I will share. Of course.
I just would like to say I really enjoyed the presentation. Thank you a lot.
Oh, thank you.
It was very. I learned a lot. Thank you. Thank you.
Thank you.
Can I ask a question, please?
Of course.
I was wondering, how did you measure the solid body guitar, the Les Paul type guitar?
Exactly the same. Exactly the same way. Tap the bridge of the guitar.
So wouldn't it be wouldn't there be an option to plug it into an amp and
of course
get a measurement that way?
You can do it, of course you can do it, but the idea there was to check what kind of vibrational output I have from that measurement. I know that the Les Paul guitar, you know, everyone knows that the Les Paul model guitar is the most dense and heavy guitar that you can imagine, and in fact the output was close to 0. And with the semi-acoustic guitar, I found some kind of output, and it was interesting. And I also have other measurements all the way up to very acoustic to slightly acoustic. There are different type of instruments, you know, the Gretsch with the trestle bracing, or other type of semi-acoustics. And of course, you can also perform electrical measurement. It has to be very interesting, but as I said, it's not my main interest, so I didn't explore a lot this possibility. But it was just a suggestion to show that you can do a lot of things with a very simple system. So my suggestion is that all of the people that are interested in guitar maker and that are interested in going a little bit deeper in understanding the behavior might invest a little bit, and the community it's already growing in this direction, but it will be growing much more in the very next future. And in fact, what for me it's very important is to all together try to define some standard, because today, if you do this type of analysis, you can sell it very easily if you want to your customer, to show what is the difference that you have compared to other builders, for example, to industrial builders, because it is sure that industrial builders doesn't make this kind of analysis. It's not because they can't, it's because they don't want, they don't find the interest, I guess, today, I guess, it's a guess. Industrial guitars are usually heavy and are not subjected to big issues with wolf tones, while very responsive guitar can have this kind of problem. So it's a good idea. And when you buy a speaker, this is an example, c'est en français encore. When you buy a speaker, you have a specification sheet that tells you the frequency response and the parameters. I would say, why not do the same things with some guitar when you can add to your specification sheet, not only the wood that you are using, but also which are the main mode frequencies, what is the frequency response, and what are the main parameters. I believe that in the very next future, we will go in this direction, because when I began building, personally, I began building guitar when I moved in France 10 years ago. I wanted to begin to play guitars again. I went to a shop, I played 10 guitars. Every guitar was the same. I didn't understand what was the difference, and I decided, okay, I'm not buying anything, because I was really not convinced. And if maybe at that time the people on the shop, instead of talking about, I don't know, I don't remember exactly, but it was not convincing. He could have been showing me a specification of instrument to explain better and to help me understand the differences. Maybe I would have bought something. Or if maybe I meet someone that explained to me what is the difference between two instruments, not just with words, but also with some technical explanation, it might be interesting. So my idea is that this is useful for the whole community, and especially for the guitar maker community, that can really make big difference with the industrial builders. And today I don't see the interest for industrial builders to go in this direction. But anyway, it's changing very quickly.
I also, if I might say, I see opportunities for repair as well, because, for example, I have a customer who bought 2 guitars of mine, but has also got a golden era classical guitar, a very nice guitar. But the problem with the guitar is it's very resonant on the A frequency, so it's producing problems, especially when amplified. So I could imagine using the system, trying to alter this for him and showing him what I did, you know. Of course.
It is very interesting, and the customer will be back. Huh? This is sure. This is for sure.
Can I ask a question?
Please.
In regard to the Chladni patterns, we're always measuring them with a very pure frequency generation, like a sine wave. But in the real world, when you play the guitar, you're subjecting it to many different frequencies at the same time. How does that work with the different resonant poles? Is there an interaction between them?
Of course, it's an interesting question. Generally speaking, in the engineering world, you have superpositions of the modes, and this is quite linear. So, of course, the whole shape of the guitar in the real world will be different, because as you said, there will be the intermodulation, superposition, and of course it will be different. But generally speaking, it's a linear phenomenon, so it should be the exact sum of all the modes. So in reality, in practice, it doesn't affect the measurements. Of course, you're measuring something different. It also might be something to investigate. It also might be something to investigate, of course. It's interesting, of course. You have to, once you begin to make measurement, you understand that each time there are slight difference. Sometimes you have very clear peak. Sometimes you see that the peak is split and there are smaller resonances. When you begin to make measurements, you have to, in fact, at the beginning, you have to take care, because when you see a lot of things, it might be a little bit, might be, I don't know what to say, might give you on the wrong way, maybe. So you have always to trust yourself, to trust your experience, and to try to look with a little bit of, I don't know what to say. Sorry, I am missing some words. But of course, there are plenty of investigation to perform, because up to some years ago, I would say, maybe 5 years ago, most of the research was performed in university and in the academy. And the academy, it's very nice, but they are interested in the physics of the instruments. They don't have experience on the real life situation. They are not interested in the relationship between the measurement and the experience. And this is really what interests the guitar maker, because in the end, we sell an experience, and we want to be, at least my curiosity is to try to master the experience, to understand what really makes me smile when I play a guitar. And in this direction, there are plenty of things to do. This is why we propose together with Fred Pons at APLG to go back to the association and to propose webinar to share these tools, because the problem is that we need to use similar tools. If everyone uses something slightly different, it's complicated then to speak to each other. So it's something like a common language. So if we begin to agree on the basis, then we can begin to share and to discuss about the things. Of course, it is interesting, the question. You might have to work on several instruments, take frequency response, analyze the Chladni patterns, try to follow changement with hygrometry and external parameters, and try to cross-relate several instruments, and maybe to start thinking also about a new way to measure the instruments. Of course, there are this is what I know and that I am sharing, but there might be also new possibilities to share to measure an instrument. I don't know if this is an answer to your question.
Yeah, thank you.
Another question. I noticed with loudspeakers that the bevel of the loudspeaker itself is a lot more flexible than the conus itself. And you can see people like Taylor, they make a small routing on the back of the top. And I think it is done with the same idea in mind, that the whole top can move a little bit better. I would think that if you would measure that, the whole top would be a lot more flexible. What would it do for your measurements?
Okay, so it is true. It is one of their patent. It is not a lot more flexible. For example, I measured a couple of Taylor. One was at 0.15, which is very, very good parameter of deflection, 0.15 millimeters, and another at 0.13. It's of course a very good value of flexibility. I guess that Taylor on the lot of the industrial builders out there is one of the most technical. So I was looking for, anyway, there is a patent that Taylor filed for this solution. It's very small. It's very small, and the effect is clearly evident, but not so drastic, I would say. So in the end, yes, usually Taylor guitars are quite flexible. Compliance is good, but the fact that you just cut this small channel on the edge of the soundboard makes that the rest of the soundboard is very thick and quite heavy. So
okay,
in the end, the Taylor guitar that I had the chance to measure were not really exceptional for, generally speaking, on a monopole mobility measurements. But then again, when you cannot master the frequencies of the main modes, it is better to be a little bit on the heavier side than on the lighter side, at least for
since you work for vocal loudspeakers,
yes.
Would you say that we can compare the top of a guitar a little bit to a loudspeaker, or is that a comparison you cannot make?
I would say so, of course. Yes.
But you in your loudspeakers, you make the edge very, very flexible. So if we can imagine that we would be able to do it on a guitar, to make the same flexibility without the whole guitar collapsing, would you think it would open up the sound more?
I don't know. One thing that I know is that, as I said before, we are building acoustic guitars in this case, and musician want to recognize the instruments. So if you make something too different, you have to be sure that there will be someone that it is interesting on your new sound. When you make a new instrument, you need a new musician. So all of this is to make better instruments or to control or to solve problems. Your idea is to make a new instrument.
Sorry.
So, yes, it might be interesting, of course. And yes, there are many similarities. It's a membrane that is vibrating. And this is also why I am so interested in this, because it is close to what I did most part of my life. And I think that there are many similarities, of course.
Jaco, I would say that we achieve that by making the soundboard thinner gradually as it gets to the edge, and also by making the bracing lower as it gets to the edge. So rather than a sudden thing like a route, it's more of a gradual. The heaviest, stiffest part of the soundboard is around the bridge, and the lightest part is around the perimeter. Yeah, it's true.
Thanks. Yeah.
Yes, when you thickness the soundboard, I guess that you don't have only the compliance, which is changing, but also the moving mass, because you are removing more material. So sometimes it is difficult to really go down with the frequencies, because from one side the table, the soundboard is more flexible, but from other side it's also lighter. So these are two opposing phenomena. So you go down a little bit, but not too much. So you have to take care, because at sometimes the table starts to moving a little bit too much, maybe. So maybe you have to take care of this. But
so you mean that as you're increasing the compliance, you're also reducing the mass. So
yes,
they're kind of cancelling each other out.
kind of, yes, a little bit,
Yeah.
of course.
Yeah.
But this is really about the tuning of the instruments, and everyone has different formulas. What I find interesting is that also for quality control, as I was saying, if you take measurement in different stage of the build, you can know that, for instance, with this type of new wood that you are testing, you are plus or minus in the values that will give you a good result in the end. So this is something that if you measure the first time that you glue the soundboard to the rims without the back on, for example, you can measure the first time the frequency resonance because you need to fix the edges, of course. When you measure the soundboard without fixed edge, it's more delicate, because the pattern of vibrations are completely different, of course, and the frequencies are very low, so it is very difficult. But when you glue the soundboard to the edges, to the rims, it starts to behave like a soundboard, and you can make the first measurements. Then you can see before gluing the bridge if it's okay or not. And with the back on, all of these stages can be monitored and can build a database that is very useful, of course.
And if we were to I'm just thinking out loud here. The question was already asked about the sinus waves and Chladni patterns, and that's not a real life situation. What if we were to take a sound of a plucked string, like impulse response wise, and loop it and use that as an exciter for the top? Would that be an idea? Do you know what I mean?
Excite the top with the sound, you mean?
I mean, what if we were to excite the top to get, like, for example, Chladni patterns with an actual plucked guitar string sound coming from the speaker, let's say, or something like that, or played with a finger. Like if you loop that sound and you take it and you use it as a frequency to excite the top.
But if you have a speaker and you have a frequency generator, it's the most simple way, I guess.
Yes, I understand, but I was just curious about if you're talking about, yeah, let's enhance the system. I was just thinking out loud and creative, maybe, just to know your thoughts about that. What if we were to do that, or take the impulse response of a violin, maybe, and put it through the speaker on a guitar, and let's see what happens? Or is that foolish?
I don't know. You might try. I didn't find the needs to investigate more in this sense. I think that this type of excitation is good for what we need. But I don't know if you will work on this, you will share your results.
Okay, thank you.
Hi, Giuliano. I have a question. Do you think we should or could look at the troughs in the frequency response as well as the peaks, or do they have no bearing?
I don't know. Yes, we have to look there, of course. We have to look there because all of these zones are very good for us, because the resonances are active in a very wide frequency range, and the more we are away from resonances, the more clean is the sound. Yes, we lose a little bit of SPL, but when you play the guitar, sometimes it's difficult to see this. What you see is that the sound is very clean, the sustain is very nice, because the sustain is minimal on the resonance frequencies, because at the resonance frequency you have the lower mechanical impedance, so all the energy from the string goes down to the table, and boom, it kills the sound. But very far away from resonances, you have the opposite results. You have very nice sound. And when you shape the sound of the guitar, this is very important. When you begin working with this type of mentality, when you begin thinking, where do I want to place my resonance to avoid wolf tones, you will see that you don't have a huge palette of possibilities. Because if you want to avoid harmonics, for example, you want to avoid 90 and 180. So you have to go 95, for example, but 95 hertz. If you think about notes, 95 hertz is, for example, is much closer to the G, which is for me, in my opinion, I don't know why, I like the G. I really like the fact, I really want to have a G with a very clean sound and with a very good sustain. When I have a resonance in between these two notes, I don't like it, because I don't know, maybe we might ask to musicians if they play some notes more than other notes, if they like some notes more than other notes. I guess that this would be an interesting field of exploration, but placing the resonances is also looking at the zone where you don't have resonances. And yes, it is interesting. It gives you also a nice indication about the responsiveness of the system, I guess. This is also something else that can be explored. Not only the maximum amplitude, but also the minimum SPL in between different nodes. It can be very interesting, of course.
Thank you.
Okay, so what I suggest is that, first of all, thank you very much, because I see that there is a lot of people, and it's very nice to be able to be in front of such a very nice platea of guitar maker. For me, at least, I consider it as an honor, so I thank you. And I would say that if you are interested, we can go on with maybe in this autumn with the next episode, where we can share our experience, or where we can talk about, for example, wood measurements also, because with this system, it is possible to measure the mechanical parameters of wood, and also the damping at high order modes of different type of wood. Because even if you have similar mechanical parameters at low frequencies, it doesn't mean that the wood behaves at the same time also at high frequencies, and it can be an interesting subject. So I am planning to publish something else for the APLG, and so if you are interested, we can set up another meeting in the next future. So we will discuss this on the forum maybe.
This is Adam. It would be great if we could go on. I have one last question.
Yes, please. Yes, please.
My question is, do you think if just to start to record it, to make some first tests, it would be possible to do it with another microphone, with a condenser microphone or something, and a sound card or something? Or is it? Do you think it should be this microphone and?
Yes, it is possible. It is possible, but I am not suggesting to do this.
Okay.
Because in fact, you have so much more with a small investment, which is really around $100, 100 euro, and you really have so much more that I would suggest to go directly with this. It's not there is nothing else needed because the software is free. You have a computer. This is very convenient. You don't have any other cable. You don't have any other soundboard. And I can tell you, when you work in the atelier, in the workshop, you have a small tiroir. You put it there, you take it, connect, measure, put it back. It's very convenient. So I would say that for me, no, I really don't see the interest. Okay. Can you do this? Yes, of course. Of course, you can do this with any other microphone. You can also use your phone, smartphone. With smartphone, it's much more difficult. There are some applications, but I really not suggest. I really strongly suggest to use Room EQ Wizard because it's a powerful software. It works very well. If you have another microphone and you want to make some tests, of course you can. It's possible, and you will get good results, of course. But I mean, it's a small investment for a professional. I mean, it's not 1,000 neither 10,000. So I suggest to go directly with the microphone. And also because usually, if there is an interest, you will see that it's fascinating. So usually it's also addicting. Really?
Yeah, I totally understand it.
There is a first period which is complicated. The first period is complicated because you will see something and you will listen to different things. It requires a little bit of time to assess, to find your position in this whole thing. But once you begin to make different, in fact, my suggestion is at the beginning, you just measure finished instruments. You start collecting data, and you don't change anything. What you do, you don't change anything because I've talked to some guitar makers that immediately began to, I have to modify this. No, you don't, because this is what you have been doing for the latest 10 years, 15 years. So you don't have to change just for the sake of a measurement. You continue to do what you do, look at the result, compare the result with your feelings, with your experience, with the perception that you have, and begin to build your own experience.
Yeah, it's much easier to have a quality control kind of. So if you say it's much easier, I would guess. So to control where the wolf tones are and where they are not, and to see them actually.
Yes, of course.
So, and also to have, if you once recorded one instrument and then built another one, and the customer wants kind of the same instrument, you should kind of want yourself to deliver the same quality, or kind of when you notice, I like this kind of mids that I hear, I like the bass. What does it show me on the graph?
Yes, exactly.
So and yeah, that's what you said. Connect the feeling and the emotion and the perception to numbers and frequency and responses. Yeah, absolutely. So I'm not shying any the investment. I just was curious if it makes a difference.
Anyway, you can try. If you have another microphone, of course you can try. All of this information are on the manual that is published on my website. I can show you the manual. I can show you the page. Okay, this is my website, and you have my research page, and in this page there are. In this case, we are interested in the first one, measuring and tuning the performances of the acoustic guitar. You can download or read online, and inside this is the most. It collects most of the things that I talked about today, and you find all of the information about the measurement system on the Appendix A, which is about the setting of the software. You have all the information about the first things that you have to do, how to set the really the measurement, the analysis. You have everything which is necessary to perform the measurements, and then some suggestion about how to get good results from your measurements. And there are also all the links and everything that you need for this. And
Giuliano, one last question from me. We don't make fully acoustics, we make semi-acoustics guitars and bass guitars. But I really like your idea of making a frequency response of every instrument as part of the spec list, so to say. Would you have a suggestion how to do this with a bass guitar, for instance? How would you're now using a hammer to excite the instrument? Is there another way to excite, for instance, a bass guitar and make an accurate measurement of the frequency response of a bass?
Are you talking about an acoustic bass guitar?
No, an electric bass guitar, for instance.
Electric, solid body.
Yeah. Solid body.
I guess that in a solid body, in a real solid body bass guitar, you don't have so much acoustic output from the body, so I don't suggest to use the hammer. You can try, but I think that you will not see a lot of things happening. This doesn't mean, of course, that the body doesn't have, of course, a weight on the output of the instruments, but it just means that you are not, you will not be seeing very interesting things with this type of analysis. It is, I guess, that for solid body instruments, it is more interesting to perform electrical measurements. So to see what is really coming out from the pickup. Maybe also to see what is happening with the top tone on the electrical output, maybe.
For my, I think that if an electric instrument sounds good acoustically, so if you play it without unplugged, you can hear already the characteristic of an instrument. Yep. And judge if it's a good instrument or if it's a bad instrument. And the rest is what kind of pickups do you put in is just another level. And I'm pretty sure that the neck has a on an electric instrument has a big input into the acoustic sound.
Absolutely. And what I'm sure of is that every instrument has its own characteristic, and I would be really interested to see in a spectrum analysis how each different instrument would look like. Of course, you don't have the modes as in an acoustic guitar, which are very clear in your face. These are the notes, but I think you can see a difference there.
You do have a mode on a long guitar mode. You do have it also on electric. And this is yes, of course, the neck has a big influence. This one you can measure. It is slightly more difficult to measure the acoustic output from this kind of mode because you have a lot of surface radiating. So, but you do have a lot of modes, of course. All of this is true, of course.
But is it possible to kind of get measurements out of plugging and kind of an instrument with kind of playing
yes, of course. Of course, you can
not
use
electrically, but
yes, you can use a Rumik wizard with your interface to measure the output of the instrument. You can measure the spectrum that is coming out by plucking or playing the instruments, of course. You can also on acoustic guitar, you can also measure the electrical output of a preamplifier system. It's also very interesting to compare different piezo, for example.
Yeah. I need to leave. I thank you so much for doing this. I think it's really wonderful. It's wonderful that you want to share all your research to all of us. I think it's really, really interesting and lots to think about for me. Thank you.
For everyone, yeah. For me too, because exchanging and discussing it always gives new idea and new perspective.
Yeah, I have to leave as well. Thank you very much. And it'd be a pleasure to, if this will go on, and also gives me
very nice. Thank you.
Input to share my knowledge and think about what might be interesting to all of you. Okay, bye.
We will, of course. Bye-bye. So, thanks again to everybody. Merci, Perrine.
Merci à toi.
À la prochaine. Bye-bye.